Hello, everybody. Welcome to my PhD presentation. I'm Reza Farahani, and today I'm going to present my PhD dissertation entitled Network Assisted Delivery of Adaptive Video Streaming Services through Content Delivery Networks, Software-Defined Networking, and Mobile Edge Computing. First of all, I would like to thank my Professor Hermann Hellwegner, and Professor Christian Timler for their constant support during this year's also my PhD reviewers, Professor Philippe Dutorc and Professor Tobias Oswald, for their insightful comments, also for their valuable time. The agenda of this presentation includes introduction. First of all, I will talk about my motivation behind this PhD dissertation, and then briefly discuss technical backgrounds and raise 4 research questions, briefly present contribution of this thesis, and then deeply dive into 4 technical sections, including 7 scientific publications published in international conferences and journals, and then conclude this presentation and shows the outcomes of this dissertation as a scientific publication. So let's talk about our motivation behind this thesis. As you know, nowadays specifically video streaming is dominating internet traffic. And many statistics shows that video on demand and live video streamings have become significantly popular. Even live video streaming will increase and reach to 17% of whole internet video traffic. So it's important to know what is the technology behind live video streaming and video on demand as a focus of this thesis. HTTP adaptive streaming is that paradigm, is that technology. Like the standardization version of that, like Dash, also Apple HLS as HTTP adaptive video streaming protocol. The strategy behind that is simple. First of all, after capturing or after recording the video, the whole video is divided into multiple small parts, we call that segment, and then encode into multiple resolution or bitrate, we call that representation. After converting into the specific type of HAS like Dash or HLS or Microsoft MSS, it is stored somewhere at the network like origin server, cloud devices, and each client can play out the specific or appropriate version of segments time by time based on preferences, based on the buffer and network condition, and adaptively shows that and increase the quality of experience, also some parameters of application QoS. Many research, also many practical investigations shows that pure client-based HTTP adaptive streaming are not optimized and cannot achieve good quality of experience. So another paradigms for covering and improving the performance of HAS introduced called network-assisted video streaming, or shortly NAVS. In this technique, a collaboration between network, also client side, can be assist quality of experience parameters for improving. So as you can see in this figure, there are 2 types of collaboration. One of that using information provided by the client side. Also another one directly network sends some comprehensive information to clients, and client can run some adaptation policy, well-educated adaptation policy, which is much more better than pure client-based solution. There are many paradigms for presenting network-assisted video streaming based on network paradigms, based on content delivery network, or emerging protocol like LLHAS, CMAF, QUIC, CMCDN, CMST standardization. Also implementation, our computing continuum nodes like cloud computing servers, fog computing servers, edge computing. Also, there are some video techniques like transcoding, caching, prefetching, super resolution in different aspects of end-to-end video streaming services. Also, there are some hybrid solutions like multi-paradigms based on content delivery network, peer-to-peer networks, which is one focus of our studies. We investigate the literature carefully and raise 4 research questions. The first one is, how can software-defined networks and content delivery networks provide assistance for HTTP adaptive streaming clients in order to improve media delivery services? As you can see, it's summarized in this figure. For instance, CDN server can send some information about cache occupancy, and there are multiple functions, even multimedia function, video delivery function implemented top of the SDN controller as a virtualized one. And then clients can use this information for making some well-educated adaptation decision, leads to improving the quality of experience parameters, also network utilization part. The second research question is in another direction. How can resources like computation, storage, and bandwidth provided by the HTTP adaptive streaming clients be used to improve media delivery services? If you remember, I presented 2 directions of network-assisted video streaming. I mean, network-assisted video streaming provided by the client side. So gathering some information, collecting some information of the client side, and using these capabilities, this information can, in an intermediate node, even can be one step forward for improving network assisted delivery streaming services and improving QoE, also network utilization parameters showed in this figure. The third and fourth research question is regarding the practical aspects of proposed network-assisted video streaming solution, how we can deploy, implement, and how we can evaluate such type of services. There are many research gaps showed in this figure regarding network-assisted video streaming services in 2 directions, software-defined network and edge-based network-assisted solution, also CDN and or peer-to-peer delivery NAV solution. For instance, implementation, not only based on simulation, but also in large-scale cloud-based environment, or even how it's possible to use all potential resources provided by the peer side, CDN side, how we can run some computational task over peer devices, considering their energy, considering their different constraint is the challenging parts that we try to cover in our publication. Also, I will present in this dissertation. So contribution of this thesis is summarized here. As you can see, these theses try to present network-assisted video streaming frameworks via emerging networking paradigms, delivery network techniques, also learning-based solution and emerging protocols. And finally, we present 7 publications called Live, Richter, CSDN, ES-Has, Leader, Sarana, and Ararat. Okay, the story of my dissertation started from this ES-Has framework for VOD scenarios, and then I improve its performance to support both live and video streaming and equip its edge devices via some video functionality like transcoding, introduce CSDN, and then go to edge collaboration idea and presented 2 papers. One of that was Leader, published in IEEE International Conference on Communication 2022, and the second one, IEEE Transactional Network and Service Management, as an extended and comprehensive version of that. And finally, I talk about services, a framework that can support both live, VOD, or even immersive multimedia. And its result was Sarana paper. And as a second contribution, I tried to present frameworks support both live and VOD scenarios in a hybrid P2P and CDN solution. Its result published in Richter in GlobCom 2022, also submitted into IEEE Transactional Network and Service Management. The name of that framework is Alive. Let's talk about first frameworks. ESHAS, and then its extended version CSDN. Before talking about such solution, I have to introduce what is content delivery network. As you know, content delivery networks just try to distribute different servers in different geographical location, like Austria, Iran, China, India, and then each content can be fetched from these servers. Users can directly contact with the nearest server and fetch the requested quality from those servers. Another direction for improving the traditional network introduced 2013, 2014 was softwareization technique introduced as a software-defined networking SDN. Instead of having both control plane, also data plane in one integrated devices like Cisco switch, Cisco router, we have a virtualized, also softwareized version of that, and SDN try to introduce multi-layer, hierarchical layer called application layer, control layer, and infrastructure layer, which is try to separate control plane and data plane from each other and put the control plane somewhere at the network called SDN controller and increase the communication with dummy devices. Data plane also provides some features like programmable network for network administrator, network designer, etc. As a complementary technology of SDN, NFV introduce. NFV just try to virtualize every functionality of the network, even multimedia functions, top of some network appliance, like even SDN control or edge devices, cloud devices, virtualize everything like routing function, switching function, etc., etc. One state-of-the-art paper that was motivation of our work called SAPR, published in 2017 ACM MMSys and then 2018 ACM TOM. The idea behind this paper was just presenting network-assisted video streaming via leveraging some techniques like SDN and CDN. So each servers, CDN server can communicate directly with SDN controller, send some information like cache occupancy, and then clients, after receiving some information via HTTP request, can run some well-educated decision and improving QoE. What was the problem behind this solution? As shown in this figure, each client should individually communicated with SDN controller, and via increasing the number of clients, even the performance of the SDN controller can be decreased, potentially can be overloaded, and number of message communicated to from SDN controller will increase as well. So for solving this problem, we just try to propose another solution using an intermediate node at the edge of the network. We call that ESHAS. So what is edge devices? When I talk about edge computing, throughout distances, mobile edge computing or multi-access edge computing. Having some servers close to the base station like G-Node B in 5G literature, and then such type of server can play as a gateway of the network, receiving information, receiving requests from the client side, also sending to the cloud devices or any network server appliance. So the idea of ESHAS is just equipping the solution presented by the SAPR state-of-the-art and try to improve its performance. So ESHAS is an edge and SDN assisted framework for HTTP adaptive video streaming via introducing virtual reverse proxy, VRP, at the edge of the network. at the edge of an SDN-enabled network. So as you can see, here is our intermediate node, virtualized server at the edge of the network. It can receive requests from the client side, aggregate repetitive requests, and send only one request on behalf of many, separated one, communicate with the SDN controller, and then decrease potentially number of messages to from SDN controller and improve the performance of the system. ES has includes three layers in its architecture. In the first layer, we have clients, also VRP, including multi-functionality called Service Optimizer module based on an optimization model, aggregation module for request, analyzing module, also aggregating, repetitive requests communicated with the top layer. Also in the intermediate layer, we have cache server, can communicate with the SDN controller via the cache map table, sending their cache occupancy in this structure. And finally, we have SDN controller at the topest levels of our architecture, including monitoring module and communicating with different entities in our architecture. We introduce an optimization model in a multi-objective fashion for not only improving the fetching time, but also improving the quality deviation and quality bitrate of each request. What I mean about quality deviation, we introduce a server segment selection policy in our optimization model. In some cases, it can serve client requests directly by fetching. In some cases, override client requests via the replacement quality, better quality instead of the original quality, and increase the fetching time in a time-slotted fashion. We thought about our research questions 3 and 4 regarding implementation, evaluation, assessment. So we instantiated testbed, designed a testbed, including 60 clients via the Zen virtual machines on the Cloud Lab environment as shown in this figure. It includes 60 clients, multi-open vSwitch, also 4 cache servers, and connected such type of topology to the SDN controller, floodlight controller, and one origin server, and using dataset, real video dataset for dash streaming. It's a brief result of our ES has framework compared to state-of-the-art SABR, also some traditional approach like CDN based, pure CDN based, that clients can connect to the nearest server and fetch the requested quality from those type of server. In 2 types of ABR algorithms, one of that is BOLA, well famous one, buffer based, and another one, SQuad, is a throughput based ABR algorithm. As you can see, ES has could outperform state-of-the-art and traditional baseline for instance, bitrate, number of quality switch, or even stall duration. CSDN tried to go one step even forward to ES has and equip the ES has edge devices via the transcoding approach at the edge of the network. What I exactly mean in pure client-based system, as you can see, client can send their request to the closest edge server, CDN server, and fetch and receive requested qualities from those type of server. In a case of cache MEC, their request directed to the origin server at the cloud layer and increased delay. ES has improved such type of service, such type of architecture via introducing VRP at the edge of the networks via, for instance, replacement quality, direct fetching, or going to the origin server. But it's not enough. What will happen if the requested quality existed in another edge server? So what will happen if we have the higher requested quality, I mean a better quality, but we can run some functionality like transcoding for converted the higher one to the requested one. So here was the motivation for introducing transcoding at the edge of the network. So we change our optimization, introduce optimization model, and even introduce some constraint for considering transcoding capability at the edge of the network, and even extend our testbed, increase the number of clients to reach 100 clients, and compare result with ESHAS, SABR, and traditional baseline, I mean pure CDN base. Even we could improve the performance of ESHAS for average number of quality switch and average number of stalls in this framework. Although we increase computation at the edge of the network, but as you can see, transcoding segment, total segment fetch, also transcode at the edge of the network, also bandwidth usage as a costly parameters is reasonable in our framework. The third framework that I introduced in this thesis called SARENA. It leveraged the techniques of SFC, service function chaining, for serving different types of video streaming scenarios. In previous models, I only talk about video on demand or live video streaming, I mean in ESS and CSD. But increasing in amount of video generated and transport via the OTT over the top video providers like YouTube, Netflix, live video streaming, immersive multimedia streaming, there are many types of video streaming, video use cases, each of which has a separated requirement regarding QoE, QoS. For instance, some of them are sensitive for resolution, some of them are sensitive for latency and bitrate. So how we can introduce such type of network-assisted video streaming solution, integrate all of them in one framework to serve different types of video services required. It was the motivation for designing SARENA. SARENA tried to use some networking techniques like mobile edge computing again, HTTP adaptive streaming as a video delivery solution, software-defined network, and service function chaining. I mean, instead of having only one type of virtual network function like proxy server, we define multiple multimedia function, chain them together, and created chains of VNFs. We call that SFC chain or multimedia SFC chains. In SFC, if you investigate the literature, you can see the orchestration, placement, scheduling, SFC definition, also VNF definition are important aspects. So we consider to define an appropriate version for each VNF, multimedia VNF. We investigate how we can connect them together, think about the scheduling aspects, define SDN controller as the orchestrator of our framework, and place some of them at the edge of the network, some of them at the CDN side. So we define 5 different multimedia VNFs. One of that again is proxy function. Another one is caching function. Is like a simple storage, can be implemented at the edge or can be implemented CDN side. We have transcoding function again at the edge of the network. We have CDN cache or origin cache as well, implemented somewhere over the CDN network. And finally, we introduce our architecture based on this figure in 4 different layers: client layer, edge infrastructure layer, I mean for the CDN side. Also, we have controller layer at the top of the architecture, including multiple modules for monitoring, analyzing the QoE, also scheduling different requests, also for checking in some situation for increasing the configuration dynamically and adaptively like serverless paradigm. So, Sarana architecture just try to, as I told earlier, connect such type of VNF together and define different SFCs. For instance, client's request can directly serve at the edge of the network or even transcode at the edge of the network. From a higher quality level, go to the CDN layer and fetch from the cache servers, fetch from origin server, or even can be fetched from the CDN side, I mean higher quality level, and then transcode at the edge of the network. We formulate the problem again as an MILP optimization model, and the objective of our MILP was decreasing the total different multimedia services serving latency. We imagine in our edge devices, we receive multiple types of multimedia services and how we can optimize such type of latency, I mean, for different live VOD or another multimedia services. So as you know, such type of optimization model leads to NP hard problem for accelerating, also for improving the time complexity. We introduce a simple heuristic solution based on introducing another virtualized function. We call that VSF, or virtualized scheduler function. So we delegate even the scheduling task to the edge devices based on two heuristic algorithms that collaborate together between SDN controller and edge servers. Regarding the implementation, we introduced another testbed including 280 elements via the Zen virtual machines. This testbed includes 250 dash players, 4 Apache cache servers and origin server, 19 backbone switches, and 45 layer 2 links, and create a topology, a realistic backbone topology, Internet MCI, and using 4G network in the connection between client side, also the cache devices, also the origin devices, using FFmpeg for transcoding LRU, this recently used cache placement policy, and ZPF distribution for video and channel access, popularity for both video on demand and live video streaming respectively. Since we wanted to test the performance of our proposed system, Sarana, for 2 different use cases, at the same time we use 2 bitrate ladder, I mean the pair of resolution and bitrate for live video streaming and VOD, as you can see in this slide. And compare this result via some baseline systems, I mean CDN assisted, don't have any virtualized function, not only at the edge or even CDN, but also in CDN layer as well. Also, we use non-virtual transcoding function enabled system. We call that NTE, and non-reconfiguration enabled via the capability of the SDN controller, and compare result in 2 types of metrics. The first set is regarding the QoE, objective QoE, the second one network utilization, and compare result with baseline approach. As you can see, for both VOD and live video streaming scenarios, Sarana could improve the performance in terms of downloaded bitrate, quality switch, number of stall duration, and comprehensive QoE model via P1203. Mode 0 also improved the latency and network utilization, improved the usage of backhaul bandwidth as a costly parameters, and even improve the network cost since improves the backhaul bandwidth. So till now we introduce 3 frameworks each of which use edge devices individually. I mean, there is not any collaboration between edge devices. What will happen if one edge device has enough potential resources for helping another edge devices instead of going to the top layer, I mean CDN devices or even origin. So it was motivation behind Leader and Ararat. One of them is published last year, ICC, another one, Transactional Network and Service Management journal as the extended version of that, Leader and Ararat. So in these two frameworks, we wanted to establish a collaboration between edge servers to use their potential idle resources for serving as clients via MEC, SDN, and again, NFV. So exact differences between Leader and Ararat is shown in this figure. As you can see, Ararat tried to improve Leader in terms of architecture, heuristic algorithms, range of experiment, parameters, even testbed that I will present in the next slide. So the architecture of Leader and Ararat includes multi-layer again. The first layer includes multi-edge devices, each of which includes the caching, also the computation for transcoding capability. Each edge device is located close to the base station, like G-Node being 5G literature. So we called one of them LES, another one NES. I mean, in our framework, we have local edge server, also neighboring edge server. That means if such clients send their request to the edge server, this edge server is local edge server for them, and this one is neighboring edge server for them. Also, on the top of the edge layer, we have CDN origin layer. Again, they can communicate with the SDN controller through the cache map messages introduced even in ESHAS and CSDN. And finally, we have SDN controller can communicate with the CDN origin layer, even edge layers for achieving some information like resource information, their request, or edge cache occupancy resources or computational resources. We call that comp map, edge map, respectively. The novelty of this solution introducing one concept called action tree. Action tree just try to illustrate all types of action can be used for serving clients' requests. For instance, local edge servers can use their partial cache for serving requests or even transcode at the edge. In some cases, they can go to the neighboring edge servers and then directly serve requests, or even using transcoding at the neighboring edge servers, or go to the origin server and CDN server. As you can see, Leader's action tree is equipped with one additional action called action 6 for going to the neighboring edge server, transcode at the neighboring edge server, sending to the partial cache of the local edge server, and then serving a client request. In Leader and Ararat, we formulate the problem in one paper, I mean in Leader, based on a single objective, serving latency. In Ararat, even we consider network cost, I mean for both bandwidth, also for computation at the edge of the network as well. Ararat tried to introduce coarse grain or CG heuristic, I mean running optimization model instead of at the top of the SDN controller, and introduce LEM or local optimization model, running optimization models or MILP at the edge of the network in a time-slotted fashion. Again, for improving the time complexity, we introduce Ararat fine grain one heuristic instead of an optimization model. We can run a lightweight heuristic approach at the edge of the network. We call that EFG. So even we think about the impact of network fairness, how we can create network bandwidth allocation and network bandwidth allocation, how uh, such type of techniques can indirectly help for improving the quality of experience, users' quality of experience improvement. So it was motivation for introducing another fine-grained solution heuristic in Ararat, as is shown in this slide. And pseudocode of this solution is shown in this slide. Is just collaboration between SDN controller, also edge devices collaborate together for further improvement of QoE and network utilization. So the fairness, the bandwidth allocation strategy is introduced via the simple optimization model, linear optimization model over the SDN controller. SDN controller can periodically monitor the network and in some cases reconfigure the bandwidth allocation to each edge devices, connected to the CDN devices. And we instantiate we design a testbed for both frameworks, Leader and Ararat, and instantiate such large scale testbed, including 301 elements via the real backbone topology. One of that is based on Giant, another one is Apliane. So we compare results via the state-of-the-art methods like SAVR, our previous work ESS and CSDN. Even we compare results via two baseline methods. One of that is Nicole, another one is Decode, by increasing or decreasing the number of actions for serving clients' requests. As you can see, Leader could improve the baseline solution, Nicole decodes in terms of bitrate, in terms of number of quality switch or comprehensive QoE model. We call that here APQ, or average perceived QoE, calculated by ITU P12 or 3 mod 0. Also, it improves cache hit ratio and backhaul traffic usage. And in Ararat, we analyze a result in comprehensive scenario in terms of both QoE parameters and, as you can see, Ararat algorithms here. Ararat FG1, FG2 could improve the perceptual QoE for two types of ABR algorithms, BOLA and SQuad. But it also improved the quality for network utilization parameters as well. So what happened for the next research question? How we can create a network-assisted solution using some information provided by the client side or even using their resources. It was motivation behind designing Richter and Alive paper. We published 3 papers based on this research question. Okay, before starting, I have to introduce peer-to-peer network instead of having, traditional client-server topology. In peer-to-peer network, each client can communicate with other client, not only based on the client, sending requests, but also it can plays the role of server as well. Also, it is too much usual in such type of architecture. One server called tracker tracks different requests to see where is the location for serving client requests. For instance, is based on the server side or is based on the peer-to-peer overlay network. So tracker server is here, receiving information regarding requests and track requests to see where is the or who is the peer or server for serving client request. Okay, so we connected CDN and P2P together to satisfy HAS client requests with acceptable QoE and improved latency. So Richter again tried to introduce such type of network assisted video streaming via not only the CDN but also via the hybrid P2P CDN. I mean, using both capability of P2P and CDN delivery network. Alive tried to improve Richter, framework via another solution, improving its action tree. I will introduce in the next slide. This is the architecture of our Alive paper. Alive includes four different layers. The first layer, I have to mention that both Richter and Alive is dedicated for live video streaming. Why? In live video streaming, latency is super important. So we just wanted to provide the services for such type of application for improving the latency QoE by imposing some computational task at the edge of the network or even P2P devices. So live camera, after capturing an event, encode and package to Dash or HLS sent to the origin server segments. And then in the CDN server, based on different models of caching, we can store different segments. And then we have edge devices equipped with a partial cache. We call that edge partial cache or edge transcoding function at the edge of the network close to the base station. We introduce some modules for bandwidth monitoring, for resource management, decision making, module. Also at the peer side, the novelty of our work is here. I mean, not only we can use the storage or simple caching strategy based on the public bandwidth, but also we can run some computational tasks at the P2P devices. As you can see here, we can run some transcoding at the peer side, or even we can go one step forward and upscale the original request to introduce PSR, super resolution at the client side. So in Leader, we just use in Richter, we just use PTR, transcoding at the peer side, but in Alive, we use both PTR and PSR, super resolution as an additional function for the P2P layer as well. So again, we use the benefits of introducing such type of action tree for Richter. As you can see, we introduced 7 different actions. In Alive, we added 1 extra action for running super resolution at the peer side as well. So again, we formulate the problem in Richter only based on serving latency, but in Alive for both serving latency and network cost as well. Richter tried to introduce a heuristic based on online learning or OL approach. It's leverage new module, use classification technique, introduce an agent at the edge of the network based on self-organizing map or SOM. The strategy behind our proposed solution is illustrated in this figure. As you can see, classification is based on the channel, based on the request, based on the quality, information of the peer side, and finally, we have multi-threads of our SOM agent here based on the feature map and running some decision making. In some cases, if our agent made some incorrect decision, even in the next run it can correct itself. It's based on online learning, reinforcement learning, and Alive even runs a simplified version based on the greedy approach introduced in this figure. Instead of having such type of complex online learning, we just introduce a simple greedy based approach here, and you can find more information in the paper. Okay, so Again, we just wanted to answer research question 3 and 4 by introducing a large-scale cloud-based environment as our testbed. In this frameworks, we had to use peer devices in a realistic scenario. So we use Apple M1, Xiaomi Mi 11, also iPhone 11 as our peer devices, and compare result via such type of baseline approach. Since there is not any peer-to-peer hybrid solution using computational resources of peer devices, we use such type of a baseline approach by decreasing number of actions for serving client requests. NOH, SEH, NTH, ECT, also NSH are baseline solution. We compared our Richter and a live paper with them. Was it reasonable to run some computational tasks at the client side? So it was our question. So we just wanted to compare power consumption, battery usage of different approaches for instance, 5 minutes video to see is it reasonable or not, and then transcode time and see, its performance. I mean, the distortion at the edge, also at the client side regarding such type of functionality like transcoding and super resolution. And then compare results with baseline solution in terms of performance parameters, in terms of QE parameters like bitrate, quality switch, number of stall duration, or perceived QE calculated by ITU P1203. Even for the network utilization parameters, as you can see, Richter could improve its competitor for all performance metrics, also network utilization metrics. And then live for BOLA, again, squad as buffer-based and throughput-based improve not only the QE parameters, but also the network utilization parameters as well. So as a conclusion, the first research question was how can SDN and CDN provide assistance for HAS clients in order to improve media delivery services? So we introduced ES-HAS and CSDN by introducing virtual reverse proxy at the edge of the network and design new server segment selection policy. Sarana tried to design VNF, chain them together, and serve different types of video streaming services via the capability provided by the SDN controller, like dynamic reconfiguration. Also, Leader and Ararat tried to establish a collaboration between edge devices, use the idle resources provided by each edge device for running some computational tasks like transcoding, and we propose an action tree as a concept for Leader, also for Ararat paper, including possible action to serve requests and propose fair bandwidth allocation to investigate what is impact of network failures on the QE fairness. For the research question, for the second research question, how can resources provided by HAS clients like computation, storage, bandwidth used to improve media delivery? Again, we introduce Richter and Alive. One of that is based on online learning methods. Another one is based on the simple greedy approach. Both of them introduce action tree, can run transcoding or even super resolution over the peer side, and we investigate different parameters to show the performance of our approach compared to the state-of-the-art solution. The third research question, what is the utility of the proposed assistant and collaboration services? We categorize our performance evaluation into 3 parts: users QE metrics, network utilization metric, also algorithms performance metrics. For the users QoE, we always compare result with quality bitrate, number of quality switch, number of stalls duration, service time, even for some objective QoE parameters like VMAF or P1203. And for the network utilization, we compare result with cache hit ratio, transcoding ratio at the edge or P2P, running super resolution at the P2P devices, computational cost, backhaul bandwidth cost, and so on. And for the algorithm performance metric, we always compare result with our MILP model in terms of execution time and objective accuracy. And finally, for the fourth research question, how can the utility of the proposed network-assisted framework be evaluated both theoretically and practically? We design and instantiate a large-scale testbed, including hundreds, tens of clients. The cloud lab environment use diverse range of ABR algorithms at the client side, employ different bitrate ladder for both live and VOD scenarios, use open flow backbone switches and float light SDN controller, use realistic network traces, tools, and assumption, and compare our result via this solution. And finally, the outcome of this dissertation, some outcomes of this dissertation are listed here as a first author publication, also as a co-author's publication. Thank you very much for your attention. I will be happy to answer your question. If you have any question, please feel free to contact me via the mentioned email. Thank you for your attention and have a good day.